Okay, welcome everyone. So before we continue further with looking at examples of sets of vectors and whether or not they're a basis for certain vector spaces or subspaces, let's take a second to crystallize an observation that we've made, which is called the spanning set theorem. And so the theorem states the following. If S is a set, an index set of P different vectors, V1, V2, Vp, and again, we kind of started this semester thinking about these as column vectors in some R2 or R3, but these are now more abstract things. These could be polynomials or matrices. But let's consider a set S of a bunch of vectors, whatever that might mean in our vector space, V, and then let's let H be some subspace of V, which is spanned by these vectors, V1, V2, up to Vp. So remember that once we pick any set of vectors in V, then the span of those vectors is going to be a subspace. And our subspace H, that very well could be the entire vector space V that we want to find a basis for. So one point here is that if one of these vectors in our set S can be written as a linear combination of the remaining vectors in S, right, then removing that vector from the spanning set does not change the space that we're able to generate by taking linear combinations of those vectors. So Vp happens to be a linear combination of V1 and V2. Eliminating Vp from this set has no effect on the vectors that we're going to be able to generate by taking linear combinations of vectors in that set. The second observation is that as long as our subspace H is not equal to the, here I have 0, this should be 0 vector. So if H contains a subspace which has some non-zero vectors in it, then there has to be some subset of vectors S which does form a basis for H. And so just to illustrate this with the example that we've looked at, we started thinking about H as the span of all of these 5 vectors, the first 3 standard column vectors in R3, and then we added this vector 1, 0, minus 1, and this vector 0, minus 2, 5 to the set. And then we looked at this last vector, and we saw that it was a linear combination of standard column vector 2 and standard column vector 3. So we can remove this vector, and we can still generate any vector in R3. We have not made any impact on the space that we're able to span. Since this vector 1, 0, minus 1 was a linear combination of the standard column vector 1 and 3, we could also remove it from this set. And right now, this set of 3 remaining vectors spans the same set that all 5 of these vectors spanned. And now we've got a basis for R3. Removing any additional vectors from this set is going to affect now the space that we're able to generate, since all 3 of these vectors are linearly independent from each other. Okay, and then one more thing to point out before we move on to more general examples is that we've seen that this set of 3 vectors, the 3 standard column vectors, 1, 0, 0, followed by the column vector 0, 1, 0, and then the column vector 0, 0, 1, which would be the set that we can denote E1, E2, E3, that this is a basis for R3, and this is probably the most natural basis that you might consider. This is the easiest one to identify, that we can generate any vector in R3 using these 3, and by adding any additional vectors to this set, it's easy to determine that any other vector that we try and attach to this set is just going to be a linear combination of these 3 vectors that we already have in the set. And so we can extend this idea to higher dimensions of vector spaces for Rn, just by adding more of these standard column vectors. So we call the basis, which consists of just the standard column vectors in Rn, the standard basis for Rn. Okay, but as we'll see, there's not a unique set of vectors which forms a basis for a vector space. We could pick different sets of vectors that still will be a basis for the same vector space. So what we're saying here is that this set of vectors is one such basis, and it's probably the most natural one. So we call this basis the standard basis for Rn. So for example, if you wanted to think about, well, what would a basis for R4 be? Well, we could take the span of 1, 0, 0, 0, and 0, 1, 0, 0, and 0, 0, 0, 1. I skipped 1, sorry, I did that out of order, and then we'll do 0, 0, 1, 0. And so this would be E1, E2, I did things slightly out of order, E3, and then E4, and this would be the standard basis for R4.